may fail. Okay, I need to close some of those. Estimation and streaming. Okay, what's going on? Okay. Oh. Okay. Any questions so far? Let me adjust this. Hello. Wait, why is this not working? Hello. This is very weak. Why? Hello. Microphone test? Okay, I guess the microphone system is broken somehow. Yeah, I should have enough power here. Hello. Okay, I guess I'll just speak louder. And anyway, now we are going to the most exciting part of our course, which is talking about how actually Shor's algorithm works. And but let's still have a small recap first. So in this chapter, we start with talking about this Fourier transform. Okay, this is a bit slow. Okay, so we're talking about this quantum Fourier transform algorithm, which is faster than classical Fourier transform, but they do Fourier transform on quantum states instead of classical data. So we'll give a quantum state as an n-dimensional vector and get an n-dimensional vector that's the quantum Fourier transform of that of the previous vector. Just like kind of like you're thinking the quantum state as classical vector and then you do Fourier transform, but they are still quantum state. And Fourier transform are those matrices that have entries that's 1 over square root n e to a 2 pi jk e to a 2 pi ijk over n. Okay, so some of the Fourier transform matrices are here. So n equal to 2 we look like this, n equal to 3 look like this, n equal to 4 they look like this. So all the entries are omega to the jk power, where omega is the nth root of 1. Okay, nth root of 1 in terms of the complex plane. That's a Fourier transform, and we find a way to do it very fast. It kind of look like this, because we see that Fourier transform computational basis state has a spatial product structure, and that means we can do those Hadamard control rotation thing. So we do order n square of those Hadamard control rotation. We can do Fourier transform very fast. It's order small n square gates. We can do Fourier transform. Sorry, we can do quantum Fourier transform. Okay, and that's exponentially faster than classical Fourier transform. And then we start to talking about what we can do with Fourier transform. That's this phase estimation algorithm. Okay. I guess not quite algorithm, but the Fourier transform can be used to do this phase estimation task, where you are given some unitary u and eigenvalue of unitary u, so some small u that's the eigenvalue of u, and the phase estimation give you an estimate of this phase that correspond to the eigenvalue of big U. So e to a 2 pi I phi. This phi you will learn from phase estimation. And the algorithm use phase keyback, so it kind of look like this. So you start with the t bits that you use to record the t bits. So tq bits here used to record the t bits or precision of your phase estimation. And so you do Hadamard, then with each bit you do this control u to the 2 to the some power on your testing eigenstate, and then you will phase key back to all those record qubits or control qubit, and then you see that this is exactly the Fourier transform of your phase, when your phase is a bit string. Okay? And so yeah, in more complete compact expression, you look at this. So you create the equal superposition of a t-bit computational state on your t qubits, and then you do control u to a k, where k is whatever computational state, basic state you have up here. And then you see that with all the phase keyback, you get a Fourier transform of this phi of your phase phi on first registration. So you just apply a reverse Fourier transform, and you will get your phase phi times 2 to the t, because Fourier transform is defined by a number between 1, 0, and minus 1 instead of 0 and 1. Okay, and yeah, so that's phase estimation when your phi is a nice binary fraction, so it's 0.j1 to jt. And then we kind of gloss over that when you are doing phase estimation on something that's not really a bit string to some precision, then we say you can still run sensing, and you just need to do a little more bits to get precision. And we skip all the proof because it's it's a bit too much detail, and so we claim that you can do the analysis carefully, and you see that you just need to add this extra log 2 plus 1 over 2 epsilon bits. So you want n bits precision on your estimation on phi, then you need t equal to n plus order 1 over log 1 over epsilon bits. Okay, and hopefully this is not too surprising to you. Okay. So it depends on how much error you allow. If you want a higher precision, then you need point bits. But if you want constant number of precision, then you add a constant number of bits, etc. And yeah, and another way to do this. Okay, so remember we are all going to use this to do factoring. And so this is one way to do analysis. Another way to do analysis is saying that actually you can get so kind of the other way to do analysis is kind of setting epsilon as a very big constant. Okay. And so here the epsilon can be arbitrarily small. You can choose your epsilon to be at 0.01. And but if you want the epsilon to be kind of large, so if epsilon is like 60%, if we allow epsilon to be like 60%, then we say we can get every bit of precision with this constant probability. Like, so we have 60% chance of getting error, but we still have like 40% chance to get a totally correct answer in b bits. Okay, so if you just use the algorithm, and we see that the probability to get everything correct is like 40%, and you can kind of just use this. And so if you get the wrong answer, you try multiple times, then yeah, you can see that if you just try this multiple times and see what number comes out most, then you can kind of also get the correct answer to t bits. Okay, and so that's a quick review about phase estimation. And bottom line is we can do phase estimation with not too many resources. So yeah, so go back to the phase estimation picture. So we can do this phase estimation thing with about poly t resource, because creating this thing is about poly t, and if you have the control u, if you have the repeated exponential thing, then you can also do this in poly t, and QFT can do in poly t. Okay, so this is very fast. Okay, and okay, so that's a small review about phase estimation. But anyway, we want to find the phase of some unitary. Okay, so what's this unitary that we want to use to do phase estimation to solve our problem? Okay, and let's go to the mathematical part. Okay, so I guess we are still a bit away from the unitary. Okay, so now we go to bit number 3 to do our factoring. So we actually don't solve factoring problem directly, so we do some number theory reduction so that we can do this order finding problem instead of doing factoring. Okay. So this is a totally number theory problem. It says that if you are given two integer x, so it's in x and n, and x is smaller than n, okay. And n you can think as something that you want to factor, okay. And yeah. So n is some large number that it's hard to find its factor, and then we guarantee that the greatest common divisor of x and n equal to 1. So that means x and n don't have cofactor, and then we want to find the smallest r such that x to the r equal to 1 mother. Yeah. And so I guess even for this problem to be true, there is already some number theory going. So you can, I think it's Fermat's-Little theorem says that if they are coprime, then there is some r such that x to the r equal to 1. Yeah. And I think we can just by counting, because x to any power is not cannot coprime to. Okay, anyway, yeah, it is some number theory thing you need to prove, but it's pretty easy to prove. That's not going to there. Okay, yeah, and so this is order finding problem. So this is r here. This is the order. Okay, so r is the order, and you want to find it. So your algorithm has the input. So if you're thinking about having an algorithm solving this, you have input x, input n, and there are parameters to satisfy those things, and you want to find r such that x to r equal to 1. Okay. And now talk about a little bit about how hard this problem is. And let's say L is the number of bits to write down n. Okay. And so it's about log n. So this is like the length of n. And this will be the problem size we consider. Okay. And so classically, we don't know any polylog L algorithm to solve this. Okay. And quantumly, we are going to show that we have order L to a cube algorithm to solve this using phase estimation. Okay. And so once again, why I want to solve this is because if you can do order finding for every xn, then you can do factoring very efficiently. Okay, so you can reduce factoring to order finding. Okay, so basically, so this is some other number theory thing that we will show at the end of this PDF. But for now, we can focus on order finding. Okay. And here is the example of what's the order of some xn pair. Okay, so actually, so we say n should be like something you want to factor, but for defining order, we only need xn to have no coprime. So that's a very easier example where n is some prime here. Okay, and so let's say n is this 7 and x 3, and let's try to find the order of x relative to this n. Okay, so then easiest algorithm is just you keep multiplying x, right? So you want to find x to the r that mother equal to 1. So you just see is r equal to 1, r equal to 2, r equal to 3, etc. Okay. So r equal to 1, you have x1, x to the 1 equals 3. That's not 1 mod 7. Then r equal to 2, you have x squared equal to 9, and mod 7 will become 2. Then x3, so x3 equal to 27. x3 equals x3 equal to 3 to a 3 equal to 27. But you can also just do, you already have the mod 7 thing, so you can just do 2 times 3 equal to 6. That will be the same result when you mod 7. Okay. And x equal to 4. Okay, so here I guess I should have I should write this mod equal thing instead of equal thing. Okay, so small difference. So every calculation here is mod 7. Okay, so here this is let's use red so I remember. This is is 3 line equal to, okay, so it's 2 times 3 equal to 6. And so then it's just doing the same thing. X4 equal to 6 times 3, that's 18, and then minus 7 become 4, etc. Then x5 equal to 5, x6 equal to 1. Okay. So finally on the 6th one, you see this thing minus 7 become 1. Okay. And a few checking, so you see x3 here, you have 6 here, which is actually minus 1. Minus 7, and so you see minus 1 squared become 1, so things kind of check out. Okay. Okay. And anyway, so here we see the smallest number are such that x to the some power equal to 1 minus 7, and that's 6. Okay. And then if you change number, then we change x to other numbers, say x equal to 2. And the n is still 7, then we'll have a different r, because the x2 is here, so 2 is actually like 3 squared, so then 2 squared is 3/4, and is 4, and 2 to the 3 will be equal to this 1 here, etc. Okay, and yeah. So that's an example of order. So different x will have different order, but our purpose now is being able to find the order for any pair of x and here. Okay. Any question about what this order finding algorithm trying to do? Yeah. And yeah, I guess and you can see things kind of cyclic here. So if you keep multiplying x more, and so if you want, you do x to the 7, then you will become 1 times x, 1 times 3, and that will be back to 1 times 3 equal to 3, and this is x equal to 1, right? Okay. And so if you just keep adding more x, then you are going to cycle through all those 6 values once again. Okay. And so that's what happens when you keep multiplying x minus 7. Okay, you have this kind of cyclic structure. You are going to cycle through these 6 values. Okay, and okay, so now we can go to quantum algorithm. So how do we use the quantum algorithm to help us do order finding? Then we need to think about the u that we are going to use. Okay, and so now things is a little bit tricky, but for explanation purpose, we now think about this ux. That's basically multiplying by x, right? This is the kind of nature we want to do this, because you see that in here you are keep multiplying by x. Okay, so how about we just have a unitary x that multiply your whatever input computational basis state to by x. So ux on y become xy model. Okay, we want ux to do this, and I actually said it wrong. Okay, yeah. So yeah, and anyway, okay. So this is not quite wrong here, but I should have put something back. Okay, and yeah. So this thing, sorry, let me think a little. Okay, that's a good one for now. Yeah. Think this should be fine. UX. Yeah. Okay. And anyway, so this thing, this thing depends on x, and x as we said, x as we said, we need x so that GCD x equal to 1. Okay, so we are still thinking about order finding. So we promise that xn is they are coprime to each other, and in that way, then xy will not equal to xy prime. Is it true? I think it is true. Yeah. I think this is true for different y. It's a little weird. Yeah. Okay. But anyway, so here the weird thing is that that get me a little confused is we are not just doing multiplication. Okay. So multiplication, if we are just doing multiplication, then that's easy. There is a classical circuit to do this, even reversible. But here things are a little weird because we are doing everything modern. Okay. And so everything modern, and so this x, y, and y and x, we are thinking some number between 0 and -1. Okay. And so this circuit might be a little hard to implement, but later we will explain why thinking about this is okay. But for now, just assume that we have some UX that will do this and that we can implement. Okay. And anyway, so back to phase estimation and order finding. Okay. And so we have UX here, and what we are going to do is we are going to phase estimation on UX, and we will get some phase of it. Okay. And yeah, so when you do phase estimation, we will get the eigenvalue of UX. So, well, the first question is what are the eigenstate of eigenvalue of UX? How does it help us finding the order? Okay, and what are eigenstate of UX? Okay. So, so what are eigenstate of UX? Or obviously 0 is eigenstate of UX with eigenvalue 1 because everything times 0 is 0. Okay, but that's not too interesting. What we are interested in is eigenstate of UX that go from 1. Okay, that's we want the eigenstate of UX on those things. Okay, so we know. So for the xn example here, we know x itself is 3, and okay, so let's use maybe green here, right? So for this example, we know there are 6 different x to some power that you keep multiplying x that will cycle through. So like a 3 here, and a 2 here, and a 6 here, 4 here, 5 here, and a 1 here, right? And so if we kind of start with ket 1 here, we know from the example up here. So we know if we start with ket 1 here and we multiply by, so if we think about we multiply this u3, then we know ket 1 multiplied by u3 will become 3. Then ket 3 multiplied by u3 will become 2, and etc. So you have the cyclic permutation that will do by the u3, right? Because this is basically just a classical computation. So you on those computational basis there, then ket 1 got multiplied by u3 becomes 3, ket 3 multiplied by u3 becomes 2, and 2 multiplied by u3 becomes 6, etc. We have those cyclic cycle. Okay, and okay, this is a cyclic cycle, but neither of those is eigenstate of the u3, right? Because you multiply u3 on 1, it becomes something else. It's not eigenstate. But we can get eigenstate out of the 6 of them altogether. Okay. Okay, so what about we just have these all 6 things equal superposition and integrator? Have 3 plus 2 plus 6 plus 4 plus 5 plus 1. Then when we apply u3, then everything cyclic permute, and then we get back to the same state. Okay. So yeah, so that's an idea to find one of the eigenvalue. So you have x1, x2, So everything is thinking about modern. So x1, x2, all the way to xr. and then this state will be an eigenstate to your u. And this state we call it u0. You will see what this 0 means very soon. Okay. And yeah, so the generalization of superposition of this 6 state. And here we are being lazy, so we should have some normalization. So here if we write this normalization, there are r state here. So it should be like 1 over square root r here, but we are being lazy, we just say normalization, you can kind of calculate yourself, so we ignore it to make the writing a little easier. Okay, so we mean the normalization. And anyway, so let's check that this is actually an eigenstate of ux. So as I say, you apply ux on this thing, then x becomes x squared becomes x cubed, etc. And xr equal to 1 because that's the definition of r. And x to the r equal to 1, so that 1 times x becomes x. And so you see that this thing is just this thing with some cyclic permutation. But you are adding vectors, and addition don't care about cyclic permutation. So this state equal to this state. Okay. And yeah. So we see that the u0 is eigenstate of ux with eigenvalue 1. Okay. So here we have lambda equal to 1 e to the 2 pi I equal 2 pi I times 0 equal to 1. Okay. And okay, so that's one of the eigenstate. But actually, say we have 6 state here, so we actually can construct 6 different eigenstate here. And now things looks a bit like the Fourier transform. So what we do is we multiply some factor of those omega onto these 6 states, right? So for example, we can multiply this omega sub 6 equal to e to the 2 pi I over 6. Okay, and but in more general terms, we have some omega equal to e to the 2 pi I divided by r. Okay, and but here we are here for ease of notation, let's assume this omega is h minus factor here. So this is so omega equal to, so we have funny notation here. So omega is our if we compare to previous slide, this is omega r to the minus 1. Okay. And anyway, so with this omega, then we can construct more eigenstate. So let's say we construct a state called u1. That is, you multiply omega on x and omega squared on x2, etc. So omega then all the way to omega to the r xr. And what happens when you apply ux on this thing? Well, then once again, x becomes x squared, and x squared becomes x cubed all the way, and x to the r becomes x. Okay. And now you compare those two things. They are a bit different, but they are different in a nice way, right? So you kind of compare the sentence. So the x squared term compared to x squared term, so it has omega squared here, and then it has omega here. And then if you compare x cubed term to x cubed term here, you have omega cube. You have omega cube here and omega squared here, right? And say you compare the x term, so it has omega to the r here and omega here, and the omega to the r is equal to 1 because it's e to the minus 2 pi equal to 1. Okay. And so how does this compare to you? You see the AB coefficient on this side is omega to the minus 1 over the corresponding coefficient. So this ux on u1 is just omega to the minus 1 times u1. Okay. Right? So it's omega and omega squared compared to omega 2. And here omega 1 is omega to the 0. So it's also omega minus 1 times omega. Okay. Okay. So excuse me. So you see that this thing, then eigenvalue here is omega minus 1, and then this is kind of why we want the minus 1 here, and so this thing, so the eigenvalue is omega r. Okay, so lambda equal to omega r equal to e to the 2 pi I 1 over r. Okay, and so we say there are actually r of those. So instead of timing omega 1, omega 2, you can do like omega 2, omega 4, etc. And the general form of doing this is you say you have us is about omega to the s x1 and omega to the 2s x2, etc. So for different s. So we have 2 examples of s here. So s equal to 0, then this is u0, and you don't multiply any omega phase. And s equal to 1, then you have omega to the 1, 2, 3, 4, etc. And if you run everything completely in equation, then we define us as this state, and we even have normalization. So we have 1 over square root r, because there are going to be r different bases here, and sum over, so k from 0 to r minus 1, then x to a k here, and then we have this omega sub r to the s times k. Okay. This we have this omega to the, this is not omega sub r, this is basically omega sub r minus 1. So we have this omega to the s times k here. Yeah. And yeah, so you can see this is very similar to Fourier transform. Okay, so this is like a Fourier transform to a computational basis state. Okay, any question so far? Okay, here is the main quantum part of the Shor's factoring algorithm. Okay, so anyway, we have the US is this state. Okay, and as we said, so we kind of already see this a little bit, but if you apply UX on US, then you get the extra exponential 2 pi I s divided by r factor. It's just because you apply UX on this thing, then you will get some permutation on k, and then you try to correct that permutation, then you get the extra phase here. Okay. So yeah. So there are different s and there are different k here, just like here. Okay. And yeah. So you see that the phase here, phase you get here is omega sub r to the s power. This is omega sub r to the s power. And anyway, if we do phase estimation on this thing and now ignore precision, then we will learn s over r, because, well, that's the phase phi here is s over r. Okay. And yeah, so if you know s over r, then you basically know r, although there are more things you need to do. Yeah. Yeah. But let's solve other problem first. Okay. So the other problem is, okay, so we have this ux that we kind of can do. But remember, when we do phase estimation, we also need the eigenstate u here. Okay? And so if you don't know r, how do you prepare this eigenstate u that's equal superposition of all those x in some period? That thing is quite impossible. Okay, and okay, and here, okay, so preparing different US is actually pretty hard. But then we use the thing that we told before, that we can use the superposition of different eigenstate. Okay, and how do we get a superposition of different eigenstate? Well, one of the state is 1. Okay, so 1 is actually a superposition of all different s together. So this is yeah, this is basically similar calculation to the Fourier transform orthogonality, and so you can check this yourself. So if you sum different s together, then So one component will all it together, and all other component will cancel out. Okay, and so 1 is actually equal superposition of different UAs. And so that means that when you do phase estimation with, so now you use 1 as this side here. So, or you use 1 as a U here. So 1 is not really any of the eigenvector, but it's an equal superposition of all those S eigenvectors. Yeah. And then phase estimation is linear, then we will get equal superposition of all different S and S over R as our phase estimation result. Yeah. And yeah, so we will get S over R with uniform random S. Yeah. And we'll later see in more detail, but so we will get a few of those, so S1, S2, S3, and then we do we get x1 over r1, x2 over r2, etc. And then from those, so we'll get those frictions, and then we can calculate R. Okay. I guess it's a little weird to say R1, R2, R3 here. So let's just say we get x1 over r, x2. Although yeah, depends on what we say. Yeah, so we get different s. So we'll get those numbers as frictions, and we'll see later that how you calculate R from this. But intuitively, you can kind of feel that, well, if you get lucky, then you will draw some. Well, I will need to say what unlucky is first, but yeah, let's see that later. Okay, question so far? Okay. Okay, and if there is no question, then I think I want to say a few things. Okay. So this I actually not too sure about. So let's say hard to implement. Yeah. So anyway, so that's the idea. I guess before we go to tricky point, let's see do people have get the idea here first. Okay. So I guess let's recap first. So we are saying that so headings on number 3 that we'll talk about later. We reduce our fitting algorithm to this order finding algorithm. And the order finding algorithm is we will try to find the order of some number relative to another number. So we're thinking about we have a small number x and a bigger number big N, and they are coprime to each other, and we want to find the so-called period of x related to this big N. And the period is smallest r such that x to the r power equal to 1. And the example is up down here. So if x equals 3 and equal to 7, then we keep multiplying x by itself. We get these 6 different numbers, and we see that when we have when we hit x to the 6, then it actually mod equal to 1 relative to 7. Okay. And okay, so we have those 6 different numbers. That's like the trajectory of x when it multiplies itself mod 7. And from here we see that we have a quantum algorithm that can find the period pretty fast. That is, you think about you construct a quantum gate that do multiplication like this. So uxy equal to xy mod n. And okay, yeah, u sub x. So the u sub x depends on x that will multiply any integer y to xy mod n. And if we have this quantum gate, then we see that when we do phase estimation, when we try to find phase estimation of its, yeah, so we do phase estimation on this ux, then we find out that we can find very good information on R. because the eigenvectors of the cyclic permutation is those all 6 stay together and A multiplying. So it's an equal superposition length with some phase vector of omega sub 6. And turns out the eigenvalues are just omega sub 6 to different powers, to a power 0 to 5. Okay. And yeah, so if you can get the phase estimation on any of the eigenvector, you can get some s over 6. And but we don't know eigenvectors, but we know a good superposition of eigenvector that is 1. Okay. So you don't need to do any calculation to get to know 1, where 1 is 1. Okay. And this 1 is actually the superposition of all eigenvectors. Okay. And I guess here we can maybe let's list this a little more here, will help us a little bit. Okay, so I literally don't need this here. It's a little, okay. So our eigenvectors here are, okay. So we have U0 here. Let's go a little slower, maybe show people. So U0 will be, okay, still meeting normalization, 3 plus 2 plus 6. Oh, it's more here. Plus 4 plus 5. I cannot move. Okay, let's do really slow. So let's try to list all 6 here. Do we have space? So our 6 eigenvector here are U0 equal to 3 plus 2 plus 6 plus 4 plus 5 plus 1. And okay. And then we have U1 equal to, okay, so we need to define omega equal to e to the 2 pi I minus 2 pi I divided by 6. And it's omega times 3 plus omega squared times 2 plus omega 3 times 6 plus omega 4 times 4 plus omega 5 times 5 and plus omega 6 times 1. But omega 6 is 1. And so plus 1. And then we have U2 equal to omega squared 3 plus omega 4 2 plus omega 6 plus omega, okay, so omega 6 is actually 1. And so back to omega square. Where are we? Omega square 4 plus omega 4 5 plus 1. And okay, but it's a little small here, and maybe let's go to to U5 here. Okay, so there are 6 different U. So the U sub S is from 0 to R minus 1. And there are 6 different U, and U5 is omega to the 5, 3 plus, and so now it will be omega to the 10, but the omega to the 6 equal to 1, so it's omega to the 4, 2, plus omega to the 3, now it's a reverse order, 6, plus omega square, plus omega square 4, plus omega 5, plus 1. Okay, so we have those 6 vectors. And now you see that when we add them together, then the one component all have factor 1, so one component will add up together and they will survive. And all other components will cancel because of the Fourier orthogonal relation. So say for example we think about the component on 3, then its coefficient is 1 plus omega squared plus omega 3 plus omega 4 plus omega 5. And the last thing will add up to 0, just like this thing we talk about. Okay. So it's this thing that we talk about. So we are adding the 66 equal partition point on this circle and they up to 0. Okay. And different than the 2, 6, 4, 5 component all have the same thing. Okay. And so that's the idea. Hopefully it gives you a good intuition about idea of those different UX. So I have R different UX, and they have eigenvalue. They have eigenvalue 1 and omega sub 6 and omega sub 6 square and omega sub 6 fifths, etc. So the eigenvalues are the omega sub r to the some power, and so you think about phi, then that's so you think about the phi here, then the phi is equal to S over r. Okay, so that's the idea. Okay, people got the idea about the eigenvector and the eigenvalues. So those are eigenvectors, and those are eigenvectors, and you have eigenvalue here. Okay, and okay, so that's the order finding idea, and then as we said, 1 is the equal superposition of all of them. So you can use 1 to put as the input to your phase estimation, and you will get the equal superposition of one of those output. Okay, and we'll see more detail later that when you get the random output here, so the output you get here, you don't actually get so as we can say. So we don't actually get S and R as output, we get S over R, so we get some fraction as output. So there is some mathematical detail that we'll deal with next class to actually get R out of those random output here. Okay, and so let's go over some tricky points here. Okay. So so 0 point I'm a little not sure right now, but I think it can be hard to implement UX without actually knowing R here. Okay, and that's kind of because we are doing this in a reversible way. I guess you can still I think you need to know R. Well, I guess that's similar to know factor n, but let's say need to know R here. Okay. I think you need to know R to do this, because this is reversible. So if you can do this, then because it is reversible, right? So if you can implement UX, you can implement UX. Let's try to do the proof here. You can implement UX, then you can implement UX minus 1 will put XY to Y. And I guess more importantly, you will put, let's keep this here. Okay, so you will put XY to Y, and so UX minus 1 will put 1 to X minus 1, which is equal to X of R minus 1. Okay. So so if you find X of R minus 1, also I guess this still don't tell you. Okay, I confused myself a little bit. Okay, so this is actually easy. So okay, sorry, confused myself. You can actually find x over -1 without knowing r. So I guess that's okay. Okay, and it's okay-ish, but yeah, but let's let's have a break, and I will think this a little bit through the break, and yeah, that's continuous class, and we'll go over what's the tricky point in doing the phase estimation. Let me think a little bit about this. Reason.
就是第5题那个 distance
哦，
这个是，我确定是不是就是当初写的时候是这样子，就是 trace 然后。
对啊，这个是题目里面的，
就是
OK。
如果我确定一下是不是我这样写是对，就是 trace 如果是长这样的话。
外负 y 正负0.101外负 y 正，看起来是这样没错。然后
我看一下，然后它打开应该是一样是这个先写，然后看一下，接下来是，
这样算出来对吧？哦，抱歉。
就是这样，然后接下来是这一项，然后这2个，就是那个，
这样写。说不定会对，感觉原来是对，感觉应该是对的。
我对了，我对，
你的对答案是对的吗？
就是
看起来可答案看起来有点不太一样。
没有，我下面可能算错，没有，我下面应该是计算有错。
OK，
我看一下，应该是感觉应该是根号2分之，我有算了，这是根号2分之 i， 然后这是负根号2分之 i， 然后这个是1。
OK， 所以看起来是一样。
我是想问，作业是3个，那如果是3个，它就是好像是，我看到作业看到是。
那作业我们写的 OK， 作业是3个，但是我们写的应该是，所以它应该是有 A、B、C system。
对，它是 A、B、C system。
所以3个的话，那你就只能做 B 的 part， 你就把 A、C 或者写起来可以很分。
就是说，
对。
假设是讲一下啊。就是
那我应该类似。
好，假设我这个 C 的话，就是可能把这个看作这边这个类似这样。
没有，你现在是要留 A、C 吧？因为它是说 trace B。
对 trace B。那所以我就是这2个合起来看起来。
对，应该是这样的感觉。
然后这个是
有点难写。
对，这2个合起来，然后当做这个这样看。
对。到底难不难啊？这样。
trace C 的话，我就是抓前面2个。
对。
然后当做这个，然后这个是 C。
对。
然后这个是这个，然后这个给这个。
对。这个到底难不难呢？我也忘了。 working. Okay, I guess let's go back. Yeah. Anyway, I guess I cannot exactly prove that this is impossible to implement. But anyway, because this has a very strong reversible property, so it can be hard to implement. Because you can implement this, then you also implement. Because here you erase this y totally. Okay, so it can be hard to implement. And anyway, in your homework, we will have something a little easier to implement that will do the that can also be used to do phase estimation. Okay. Okay, so that's homework. And yeah, so yeah, instead of this everything disappear, then we have some addition thing. Okay, and okay, so that's like zero's tricky point. And now go to the other tricky point that we deal with more carefully here. The first one is the one we've been talking about. That is, you want to do phase estimation efficiently, then you need to do this ux to some exponential power efficiently. And that can just be done by squaring repeatedly. Okay. And then the second one is is that we have error in our phase estimation. Okay. So we are not going to get this S over R exactly. We are going to get, so what we're actually going to get is this bit string thing, right? So we are going to get some, okay, so let's scroll to somewhere better. We are going to get this bit string thing, so we are going to get some binary fractions to some precision. And that will not be, say, something like 1 over 3. Okay? And and to do this, then we will use interesting algorithm called continuous fraction. That will give us actually a fractional number out of some number that's closer to it, if we know like some bound on this R. Okay, and finally, finally there is this problem such that even you get this 1 over 3. Fraction 1 over 3 here, you might still don't know your R, because X and R can be not coparent to each other. For example, the example up here we have R equals 6, but if your uniform random S is actually equal to 2, then you will get 2 over 6 equal to 1 over 3. But our phase estimation don't tell you what this exact S and R is. It only tells you it's 1 over 3. S divided by R is 1 over 3. So you don't know where your S and R is 1 over 3 or 2 over 6. Okay? And to solve problem, then what we do is we draw a whole bunch of different S and R. So we have a different fraction as xi over I. And then we will do this common multiplier between all those I, and we'll show that with high probability we will get the R that's actually the period. Okay. Any question? If there's no question, then let's see how do we deal this one by one. Okay. And the first one is repeated squaring, okay, or called modular exponential. And let's see these as an example. So let's say we want to compute a pretty high power of x. We want to compute x to a 17. And as we say, if we keep doing multiplication, then this is pretty slow. So we need to do x times x times x times x is 17 times. And so we need to do 16 multiplications. Okay. And but if we do repeated squaring, then we can do less number of multiplication to compute this number. So basically we write the 17 as a binary string, as a binary representation. So we have 17 equal to 16 plus 1. So we just want to multiply x16 with x1. Okay. And Then this x16 part, we don't actually need to do multiplication 16 times. We're going to do x multiplied by x equal to x squared, x multiplied by x squared multiplied by x squared equal to x4. Then x4 multiplied by x4 equal to x8, and x8 multiplied by x8 equal to x16. So yeah, so instead of doing 16 multiplication to get this x16, we only need to do 4 multiplication to get to x16. Okay. And then finally get x17, you just do x16 times x, another multiplication. Okay. So you see that instead of 16 multiplication here, you only need to do 5 multiplication, 1, 2, 3, 4, 5, to get x17. Okay. So you see that to get x to some large power r, you actually need to do much less multiplication than you think. Okay. So in general, x to the r can be done in order log r multiplications. Okay. Okay. And you can do some calculation and see that you only need order L cube calculation operation to do your control x to the j, every one of them. So the control x to the j we are talking about is this thing. Okay. So this thing with the repeated squaring, then we only need log L to the cube, basically log t to the cube here. Okay. Oh, not log to the cube, sorry. Order the cube, so order t to the cube here, instead of like 2 to the t. Because here, if you do the control u, okay, so it's basically this thing here. So if you do every control u here, so if you do every control u here by just do control u one by one, then you need 2 to the t control u here. But if you can do this thing with repeated squaring, then this only need order t calculation in control u, and so that's much faster. Yeah. So this thing can be, I think it's actually order t square only, but or order L square, but anyway, order L square is less than order L cube, so it's order L cube. Yeah. Okay. And so that's one problem solved. So we can do the u to a 2 to a t minus 1 pretty efficiently with order t operation by just because it is multiplication, then we can do repeated squaring. And then the next one is a continuous fraction algorithm. Let us get a fraction, or excuse me, let us get a how do I say, pretty good fractional number. Okay. And so we don't have detailed proof, but we'll see example. Okay. And anyway, so what we'll do is we'll take our t equal to 2L plus these log epsilon terms, log 1 epsilon terms, 2L plus 1 plus these log 1 epsilon term as a number of qubits in our phase estimation. Okay. And we came from previous slide. So if we use this many bits to do phase estimation, then we have 2L plus 1 bits precision, and with error probability 1 minus epsilon. Okay. And anyway, so now we do phase estimation, and we get the 2L plus 1 bit, and bits precision number. We have the 2L plus 1 bits. That's our estimation on side. Okay, and okay, so I guess we overload the notation a little bit, but this 2L plus 1 bit is our estimation to S over R, so this is some fraction. And yeah, so we have the psi is like some 0.J1, J2 to J sub 2L plus 1. Okay. And so we know psi is pretty close to S over R, but how do we find this S and R? Okay. And here we gave an example of this continuous fraction algorithm work, and it's like this. So let's say our psi is Okay, so we don't use a binary string, but it's similar in binary or decimal. Okay, so our size is 0 to 0.25001, let's say, and because you can always convert your binary string to decimal string with a finite bit. But anyway, so let's say psi equal to this thing, and you see this is very close to 0.25, and you think maybe it's 1/4, right? And well, this is 1/4, but so when you eyeball this, you can say this is 1/4. But how do you tell a computer to tell you this is 1/4? And that's where you do continuous fraction algorithm. So the way this algorithm works is first you get this 25001, the 0.25001, you write this as a fractional number. So this is 25001 over 100000. Okay. So nothing happened here yet. And now you do this funny thing where you flip the fraction around. Okay. So this is 25001 over 100000 is, so you flip this around is 1 over, then now you flip this 100000 and 25001. Okay. Okay, so you flip this around, and now this is a fraction, and now this is a fraction here, and you actually do division on it. Okay, so you think it is a fraction. Well, it has a larger number on upper and a smaller number on lower. So you actually do division here, and you get 3 plus this small number. Now it's 24997 over 25001. Okay. And then you keep going. Now you have a smaller than 1 number here, then you flip it around. It's 1 over this 25 something over 24 something. Now this is again a number that's bigger than 1, then you actually do a division, and you have an integer part that's 1 and the remainder part. Okay, but now you see that this division you do now has a very small part. It's now 4 over 24997, and here things are a little fuzzy, but basic algorithm will have some cutoff depending on like how big this is or how many levels around, and yeah. So the algorithm will say you see something very small, then you discard and stop here. Okay. So you see that now this fraction thing is something very small, so maybe I need to stop here. Okay. And I stop here and I discard this part, and then I calculate back all other things. What is this fraction? So it's 1 over 3 plus 1 over 1 here, and so it's 1 over 3 plus 1 is 1 over 4. And yeah, so this is not very rigorous presentation of the continuous fraction algorithm. So, but the idea is that you keep flipping your fraction number and getting some quotient and the remainder, quotient, remainder, and when your remainder is very small, you stop, and then you add everything back, and you will get a pretty nice fraction. Okay. And yeah, so in general, you will get a continuous fraction over psi that is in this form. So a0 plus 1 over a1 plus 1 over a2 plus dot dot dot. Okay. And so here we just gloss over how this algorithm actually work and why it work. We just have something that cannot works. So we say that. Well, this is more like a condition for this to work. Okay, so for this algorithm to work, we need so remember, so back here, so we want to find your S over R from psi. So obviously your S R over your psi need to be pretty close to S over R to find this. Otherwise, you might find something else, right? And so here, basically, this theorem says how close it needs to be. So if you want to find this S over R, then you need your psi to have precision basically R squared. So the distance between your psi and S over R need to be less than 1 over 2 R squared. Okay, so this makes some sense. Well, we will see more intuition in homework. Okay. So yeah. So it says if you satisfy this equation, then your side is close enough, and we just say continuous fraction of so the continuous fraction algorithm, then we'll find S over R for you. Okay. And yeah. And so there is unspecified terminal condition here. So you need to terminate it at somewhere. And I would say you will terminate it at about order L level. Okay. And so I guess order L, and L is like L, yeah, order L, so L is like a log R level. Okay. And yeah, so that's the continuous friction. And okay, so we have a theorem here, and finally we're back to just saying that the number of bits we take is enough. Okay, so the number of bits we take, we have error probability epsilon, and we'll get 12 plus 1 bits precision. And 12 plus 1 bits precision means that our error is 2 to the minus 12 minus 1. And okay. And yeah, and R is less than 2 to L. So remember 2 to L equal to 1. So here we use, I guess I can write here. So 2 to L equal to N, and that's greater equal to R. Okay. And yeah, so this 2 to L plus 1 bit precision is enough, and is enough to apply this theorem, and we say that continuous fraction algorithm can find this over R. Okay. And then you will see this in a few more detail, although you will still not have the full proof. So in homework, we will have a partial proof of theorem. So basically, we are going to show why this 1 over 2R squared number makes sense here. Okay, yeah, and yeah, so you are going to show that if you have a 1 over 2R squared here, then the S over R you can find here is unique, but obviously that's only part of the proof. So there is some S over R for you to find here. Then, if you want this theorem, you need to show that the continuous fraction can actually find it. Okay. But yeah, so that's about finding S over R. Okay. And anyway, this continuous fraction algorithm, as we say, will take about order levels, so about order over 10. And so that's still inside our order L cube thing. Okay. And so finally, the last part we need to deal with is finding R from different R1, R2. Okay. Okay. So our notation is a bit funny here. Okay. So we kind of change notation here, or we have been using different notation, but we didn't say. Okay. Okay. So we change the notation a little bit. So let's say we have a R we want to find, and we have a uniform random. So instead of S, we say uniform random S prime. Okay. And then the number we find from continuous fraction will call the S1 and S is S1 over R1 and S2 over R2. Okay. So what are we doing here? What we are doing, we are trying to say is S1 over R1, S2 over R2 that are co-prime to each other. So this is after you define all the factor. So this is deal with the thing like saying, so maybe S1 prime equal to 2 and R equal to 6. Then S1 over R1 will be like 1, 3, because continuous fraction only tells you what the good fraction is, and it will not tell you this thing. Okay, and similarly, then maybe S2 prime equal to 3 and R0 equals 6. Then you have 1 over 2 here. Okay, so I guess I didn't say, right? Yeah. So here I should say, so those unprimed ones, we are thinking they are coprime to each other. So, how should I, there? So, yeah. So, S1, let's say, for different I. So for this notation here, we are thinking for Y, Si, Ri, coprime. So we find the best fraction here. Okay. And okay, so now we have this R1 equals 3 and R equal 2 here. And how do we find the R? And the thing, the way we do this is we'll only take two of them and take the least common multiplier, and you will have a pretty good probability, constant probability, to be R. And so we can just keep doing this. We just keep getting two of them, and each time we have 1/4 probability to be success. So in constant time, then we can get R, because we cannot get something else bigger than R. So the biggest one you get here is the best one. Okay, and yeah, so we have another example here. So we still have I equals 6, and yeah, so maybe S1 prime equals 3, S2 prime equals 4. Then your S1 over R1 is 1 over 2, and S2 over R2 is 2 over 3. And here you still see the least common multiplier is 6. Okay. And okay, so then now we need to prove this weird probability. So what is actually a probability that the least common multiplier of those two things is R. Okay. And okay, and then now we need to do some funny number theory probability thing. Okay. And anyway, so the proof that is a little incomplete is this. So we basically go through all possible prime Q, and see whether your R1 and R2 is bad with respect to that Q. Okay. And okay, so I guess the second line is more important. Okay. Okay, so let's have like a break it on the first line. Okay. So the first line this line is an important concept here. Okay. So what are the bad R1 and R2 that give you that don't give you back the good R here? Okay. So the bad R1 and R2 that don't give you back R is when they yeah. Okay. So I guess beta R1 and R2 correspond to beta S1 and S2. So we are doing S1 prime and S2 prime. So we are doing analyze on S1, 2 prime, and S2 prime. Okay. So now think about what the S1 and the S2 prime do here. So when we go from R to R1, what happens is R and S1 has some cofactor, and R and S2 has some cofactor to become R2, right? So R1 is R divided by the cofactor between S1 prime and R, and R2 is R divided by the cofactor of S2 prime and R. And so really the bad case only happens when S1 prime and S2 prime has the same cofactor to R. So like both of them will take out that factor from R, and so when you do least common multiplier of R1 and R2, you don't get back to the 4R. So for example, a bad pair will be like so like a bad pair will be like S1 prime, S2 prime equal to 2, 4 here, right? So they have both of those factor of 2 here, and so they will both take this factor of 2 out of R, and so R1 and R2 will be both 3, and then when you take a least common multiplier, they will become only 3 instead of 6. Okay, and yeah, I think it's pretty intuitive that this is the only bad way this only case that bad things can happen here. So think about bad S1 and S2, then they must have some common factor. That's also common factor with R. So we have some common factor, and that factor has some prime component. So there exists some prime that divide S prime and also divide S2 prime. So we kind of denote the factor as this. So this means that Q divides S1 prime, and it means that Q is a factor of S1 prime. Okay, so Q divides S1 prime, Q divided by S2 prime, and Q divided by R. And we actually don't need to use this Q divided by R condition here. We only need to use these two things. Okay, and okay, and anyway, so if we have those two things here, then we now calculate what's the probability of. So now we think about we draw S1 prime and S2 prime from 0 to R minus 1, right? Remember the uniformly random draw from 0 to R minus 1. Okay, and so now we fix the Q, and we think about what's the probability you draw those uniformly random S1 and S2 prime. Then S1 prime will be divided by Q, and S2 prime will be divided by Q. And because those two draws are independent, then obviously it's a probability. Both of these happen is just the probability multiplying each other. Okay. So it's the probability Q divided by S1 prime, the probability Q divided by S2 prime. Just because S1, so here it should be prime. So here we are using S1 prime and S2 prime and drawn independently. Okay. And okay, so now you think about what's a uniform number. We'll get it by divided by some prime Q. Here we don't even need to use Q as a prime, but I guess we never use Q prime. Anyway, Q prime is even better. Yeah. So what's the probability that S1 prime will divide by Q? Well, that's about 1 over Q, right? Actually, it's a little smaller. Why is this true? I think it's actually a little larger. But no, it's actually a little larger, but I guess we can pick a big O here. So here, I'm a little confused. Q divided by R, why we have this equal to? Okay. 5. I guess okay, the detail is a little annoying, but so the detail about this is a little annoying. How do you prove this is less equal to? I guess we have time, but let's go over high level first, right? Okay. So on high level, well, when you divide something by Q, then the possibility is like a 0, 1 to Q minus 1, right? And so it's about 1 over Q probability to get. So it's about 1 over Q probability your number. So you have a uniform number, then when you divide by Q, then the remainder is also a bit uniform, and yeah, yeah. So the remainder is also a bit uniform. So yeah. So it's about 1 over Q probability to get this 0 remainder. Okay, so it's 1 over Q probability, 1 over Q probability. So you multiply both two, then it's 1 over Q squared probability. Okay. Okay. And then the probability of bad Q exists. Now finally, then now we are actually going through all prime Q. So this is a fixed Q. And we need to go through all possible prime, and then we just do union bound through that. So we just sum through all possible prime with this base probability. Okay. And yeah, so you sum over Q O prime 1 over Q squared. And well, then this is less equal to if you sum over everything squared, so you don't even need the Q prime here. So you just sum over Q everything here, and that's Q from 2 to infinity over Q squared. And you can show in homework by some calculus thing, then this is actually a bounded number, and less than 1 over 3 over 4. Okay, so the probability of basing happen actually less than 3 over 4, so that you can find R from R1, R2 with probability bigger than 1 over 4. Okay. Any questions so far? And okay, so let me think a little what is this less or equal to. So you are counting as 1 from 0. I think this is actually equal to. I'm not sure what is less or equal to. I will check later. So Q divided by R. If Q doesn't divide by R, then 0, 1. Okay, so Q divided by R, I think is actually equal to, because say S1 prime is in 0, 1 to R minus 1, right? 0, 1 to R minus 1. And Q divided by R, so this is some multiple of Q. So I think this is exactly 1 over Q squared. But anyway, that will also be less or equal to. And if we ignore Q divided by R, then because we are counting from 0, I think the probability will actually be a little larger, although it's like older. Okay. Okay. But anyway, that's a minor detail. That's not very important. So we have a good time to do recap here. No? Okay, so those are how we deal with the 3 issues in factoring. Okay, so let's see once again. We have 3 tricky points about, okay, not quite factoring, order finding. Okay, so the 3 key point, we need to implement all the UX to some exponential power very fast, and we do by repeated squaring. And the second is we need to deal with the error in phase estimation, and we use continual friction to actually get S over R. And thirdly, when we get S over R, we actually get some SI over RI that's SI over RI such that this RI is not really R, and then we zero that we can find the HOR by doing this common multiplier between different R's, and you have a very good probability of getting the HOR just doing a few these common multipliers. Okay, and so that's order finding. Okay. And that's all the content part. I guess it's good to do review on the content part again. Okay, so the review of the content part is we want to do order finding, and the order is like how long does the number takes when you keep multiplying itself to become 1 mod some bigger number. So here with the example of x equals 3 and n equals 7, and you keep multiplying is x with 3, and you find out after 6 times it go back to itself. Okay, 1, 2, 3, 4, 5, 6. I guess not go to itself. So After 6 times, then is then equal to 1 minus 7. And on the 7th time, we're back to 3. And because of multiplying 3 has this cyclic permutation, then we see that take some, I guess, Fourier superposition over those 6 states. Then we will get eigenstate to this multiplying unitary. Okay. And so we have those 6 different, or in more general terms, so these are R state here. Then we can find, so we have R state here, and we'll find R eigenstate. That's a superposition of those R state with different vector of omega. And the eigenvalue will be e to a 2 pi I s over r. And so the phase here will be s over r. Okay. And then we do so we do phase estimation on those eigenstate, or the equal superposition of those eigenstate, that's 1. Then we get a random OS over R, and with all the tricky point dealt with, then we find out that we can find R very fast in this order L cube time. We can find this R in order L cube time with this quantum order finding algorithm, which is basically doing phase estimation. Okay, so that's the quantum part. And okay, so that's a recap on quantum part. And if there is no question, then let's go back to classical part. So now it's a little annoying. Now we are going to talk about things that has basically no relation to quantum mechanics. We are talking about quantum theory. Classical number theory, and how do we actually do factoring from the order finding problem? Okay, so we say that we can do factoring by do order finding, but we don't have too much time. This is a bit complicated, so maybe we'll just do a little sketch here, and maybe we'll just do sketch here and stop. Okay, so how do we do factoring by doing order finding? So this is actually well known to mathematicians. Peter Shor come up with a factoring algorithm. Okay, so Peter Shor basically knows this, and then he noticed that quantum Fourier transform can be used to do order finding very fast, and that's how he discovered the factoring algorithm. I guess actually that's not quite true. He do discrete log first, but also it's still also well known to mathematician that discrete log is related to factoring. Anyway, back to math. How do we do factoring by doing order finding? So now we need to get x and n. Okay. And so first you pick some x coprime to n. So n is the number we want to factor. And okay, so first it should be easy, because so you just pick whatever random x that's less than n. And if it's not coprime, then you only find a factor of n, and you win. Okay, so you pick some random x that's probably coprime to n. And then you find, so you pick, let's say random x, let's use red here. Pick random. Okay. And you now have x and n, and then you do period finding. As we say, we want to do period finding. Okay. So we find this period R here. Okay. And so now things get funny. So depending on what R you actually find, you will do different thing. Okay. And so if R is odd, then you are unlucky. Then you just try different random x and try to get R that is even. Okay. R is odd, then there's nothing much you can do. Okay. And okay. And so there's a theorem show that R is even with constant probability. So you only need constant to try to get this R even. Okay. And if R is even, then you can do this funny thing. You can compute the square root of 1, kind of. So you can compute x of R over 2, because r is even, you can compute like r over 2. Okay, and so r is maybe a large number, but remember we have a repeated squaring, so if you know r, you can compute x r over 2 very fast. Okay, and yeah, as we say, x r over 2 is kind of the square root of 1, because we know, well, x r over 2 square equal to 1 then, right? Because x to the r equal to 1. This is just x to the r. And then we do this interesting formula. Then we move 1 on to this set of equation and factor it. Then we see x r over 2 minus 1 times x r over 2 plus 1 equal to 0 then. Okay. And okay. Now you think about n equal to some pq, right? Okay. So yeah. So remember, we want to factor n. So let's say n equal to just some pq. Makes things a little easier. Although in general, if n has more factor, then it will be harder. But let's say n equals to some pq with pq prime. And now we have 2 terms here that will multiply to basically n, right? Because they equal to 0 then. So this is some multiple of n. Yeah. And so now we think about how this pq factor can distribute it between those 2 factors. Okay, so I guess here this is not exactly true, because you can have extra, because this is not equal to n exactly, this is multiple of n. But you can kind of feel that there are 4 cases that you can distribute pq between those 2 things. And so the first one is this part has both pq, so this part is equal to 0 and this part equal to 1 and okay, and and so pq goes here, then we are saying this part is 0 and and this means SR over 2 has equal to 1 and this is impossible. This because this case says that well, R over 2, then by this equation, then R over 2 is a period of x, but R over 2 is also smaller than R. Then R over 2 will be the actual period. So that's impossible, because we say R is the smallest possible number such that x to R equal to 1. Okay, so this case cannot happen. And what about second case? So PQ is here, so this part actually equals to 0 then. Okay. And okay, so this is another bad case. So we have 2 bad cases here. So first is you need to draw R out, and the second is you don't want a PQ both on this XR over 2 thing here. Okay. So in this part, you will have XR over 2 equal to -1. Okay. And this will happen with constant probability. You are just unlucky. Okay. And then finally, you have 2 other cases. Okay. Okay. And the 2 other cases is PQ are evenly distributed between this one and this one. Okay. And then basically you can, okay, so both of them have a non-trivial factor to n, and you can then just take say you take the first one, you take this XR over 2 -1, and so you have a factor p here but don't have a factor q here. So you contain factor p, and so it's not coprime to n, and but also not multiple of n. Okay, and so when you take a greatest common divisor between XR over 2 and XR over 2 -1 and n, then you will get this p or q here. Okay, so those are the good cases. And yeah. Okay, so in those 2 cases, you see that XR over 2 -1 has a non-trivial factor to n, and you can calculate it by calculating this GCD greatest common divisor between xr over 2 and n, and xr over 2 minus 1 and n. And GCD can actually be calculated very efficiently. So we don't know how to do factoring efficiently, but if we have two things, then we can find the greatest common divisor very fast. It's by the so-called Euclid's algorithm. And I think you should, yeah, I guess, do we have it here? We don't, it's on the next slide, yeah. But the algorithm, I'm not sure. The algorithm. So how many of you actually heard about Euclid's algorithm? Is it probably something that you do in algorithm class? No? How many of you know how to calculate algorithm? But I think you actually, have you? Yeah. So this is the algorithm that you actually should learn in elementary school. I think, yeah. So you have two numbers and you want to find the greatest common divisor between them, you just keep dividing each other. So say you want to find the GCD 7, 3. And then you just keep dividing the bigger one with the smaller one and find the remainder. So you have 7 equal to 3 times 2 plus 1. And then you have 1 here, then you know the greatest common divisor is 1. And let's say, let's get a harder example. Let's have GCD, let's say 21 and 14. And so you have 21 divided by 14. You do like, let me maybe say this. So 21 divided by 14 equal to 1 plus, okay, so this is bad because you will want to do the, yeah. So 21 is 1 times 14, yeah, 1 times 14, and okay, plus 7. Okay. Also, I guess here you actually finish your algorithm, you need to do one more step. Then you need to do 3 equal to 3 times 1 times 3. And so now 1 divided by 3, 1 actually divides 3. Then you know this 1 is the greatest common divisor. And this 21, 14, then you do 21 divided by 14 is 1 plus the remainder 7. And then you have 14 equal to, oh, I'm doing this in funny way. Okay. Anyway, so this is 2 times 7. So you know this 7 is the greatest common divisor. Okay. It's called 辗转相除法 for the elementary school net. Okay. Yeah. Anyway, you have this algorithm of the very fast. You can find the GCD. And there were 2 more minutes, so I guess we can stop here. Here we just have some theorem that arguing that the 2 constants here are actually constant. Okay. Yeah. So, but we don't prove, so they don't say too much. So the theorem down there just saying, is just trying to argue that those things are actually constant probability. Okay. Yeah. And yeah, so that's a sketch of Shor's algorithm, and it's not too much different from the details algorithm, but we will talk about details factoring algorithm next time. We'll deal with some special cases. Okay, so see you on Tuesday.